Hi students, today we are going to talk about capacitors. Have you heard of the term capacitors earlier? Capacitors are very interesting devices that we'll study about in electrostatics that have many daily applications. For example, take the flash system of your camera for instance. These two plates that you see on your screen are used in the flash system of your camera. Similarly, capacitors are used in sophisticated timers. When they time all those events in the Olympics and the Asian Games, the timer they use has a capacitor in them. Capacitors are even used, in lowering and increasing the volume of your radio system or your audio system. So basically, capacitors are devices which are used in most everyday appliances, but we hardly get to see them or learn about them. So let's do so today. Capacitors. First of all, what on earth is this capacitance? To understand capacitance, consider this conducting body that you see on your screen. This one in bronze color. Now let's say that this body has an electric potential V initially. Now what will happen to this body if I keep adding a charge Q to this body? The electric potential of this body will keep on increasing, isn't it? So if I add a charge dq to this body, the potential of this body will actually become V plus dV, isn't it? An increase in charge by dq causes an increase in potential by dV in any body. And that is where the term capacitance comes in. Capacitance is the amount of charge to be added to a body to increase its potential by 1 volt. So if you take any body in the world, capacitance basically refers to the amount of charge that must be added to that body to increase its potential by 1 volt. So you can say that capacitance, which is represented by the symbol C, is simply dq by dV, the amount of charge to be added for a certain increase in potential to be obtained, isn't it? Capacitance is the intrinsic property of a substance. What this means is that it does not depend on the amount of charge being added to a body or the actual potential of a body. It depends on the body itself. If you take a sphere, it will have different capacitance. If you take a plate, it will have different capacitance. If you take an unevenly charged body made of copper, it will have different capacitance, isn't it? Capacitance, the ability of the body to increase its potential when charge is added to it, depends on the shape, size and material of the body. So let's say you have this disc that you see on your screen. When I add a charge Q to this disc, the electric potential of this body increases by 3 volts. But if I change the shape of this disc and make it something like this, in that case, adding the same charge Q to this body might actually increase the potential of this body by 5 volts. Interesting, isn't it? Capacitance determines by how much the potential of any body will increase when a charge Q is added to it. Understood? So that is the essence of capacitance that you must understand. So this also means that if the capacitance of a body is high, then a lot of charge must be added to that body to increase the potential difference of that body by a small amount. Now we had just studied that C, the capacitance, was equal to dq by dV, isn't it? We can take dV to the other side and then dq will be equal to C dV. We can then integrate this expression on both sides and say that integral dq is integral C dV. So now when there's this body here, say this one, at a potential V. In that case, when we keep on adding a charge dq to this body, so that its potential becomes V plus dV and then it keeps on increasing like that, the net capacitance of the body is assumed to be constant in this process. So we generally assume that the capacitance does not change when charge is being added to the body, isn't it? After all, as we just discussed, capacity is the intrinsic property of a body, so we can assume capacitance to be constant. If capacitance is constant, then integral dq is equal to C integral dV, and that means that C is Q by V. So in general, instead of writing C equal to dq by dV, we can always say that C is Q by V. This is an expression that you must remember. There is, however, a special case when C equal to Q by V does not hold true. This happens when you're charging a soap bubble. Let's say this is a soap bubble. A soap bubble. Now when you charge a soap bubble, what happens is that as you keep on giving charge to the soap bubble, the charge increases, plus q plus dq plus q plus 2dq and so on. But as the charge of a soap bubble increases, the mutual repulsion inside a soap bubble also increases, and this leads to the expansion of the soap bubble, like this. So as you keep charging the soap bubble keeps expanding. Interesting, isn't it? But this happens. What this means is that in case of a soap bubble which is at a potential V, when you keep adding more and more charge to it, the soap bubble takes in that charge and the potential of the soap bubble increases, but the size of the soap bubble also increases. And because the size of the soap bubble increases, the capacitance of the soap bubble also increases. So you cannot add charge to a soap bubble without actually increasing its capacitance, because the size of the soap bubble is increasing. So only in the case of a soap bubble you cannot say that C is Q by V, because in that case when you say integral dQ is integral C dV, in that case you cannot take C out of the integral. That's because the capacitance also varies as you keep on adding the charge to the soap bubble. This is the special case of a soap bubble, but in general you can always say that C is Q by V. The unit of capacitance is farad. Now what is a farad exactly? A farad is simply 1 coulomb per volt. As you can see, capacitance is charge divided by potential difference. So 1 farad is 1 coulomb per volt. Generally we talk in terms of microfarads. That's because, as you already know, coulomb is a very large unit of charge, and therefore so is farad. So we have capacitors with a value of 7 microfarads, 10 microfarads and so on. Now before we study about the different types of capacitors, about how capacitors actually look like, and how to calculate the capacitance of bodies, let us study some important points which you must know before we study in detail about capacitors. Okay? So let's start off with the first important point. You see, I just told you that capacitance is Q upon V. When I said Q upon V, what was V? V was the potential with respect to which point? Was it the potential with respect to infinity? Was it the potential with respect to another part of the same body? What was V? In general, we consider two terminals in the system whose capacitance we are calculating, and then we calculate the potential difference between these two terminals, and that is the potential difference that we use to calculate capacitance. Understood? So by convention we take two terminals in the body and then calculate capacitance. This of course is true only when it is possible to take two terminals in the body. Let me give you an example. These are two parallel plates that you see on your screen. In that case, V will actually be the potential of one plate with respect to the other plate. So when I say that the capacitance of this system here is Q by V, in that case what I mean by V is the potential difference between these two plates. So the capacitance here represents the net charge that must be added to this two plate system to create a potential difference V between these two plates. Understood? Similarly, you can consider a spherical shell and another spherical shell surrounding it. Now if the potential difference between these two spherical shells is V, in that case that is the V that we will use in the formula for capacitance. So again, if you can say that the capacitance of this two spherical shell system is Q by V, in that case Q represents the net charge that must be given to the spherical shell system, so that the net potential difference between the two spherical shells becomes equal to V. Understood? The concept of capacitance might seem to be very new and very intriguing to you at first, but just keep on with it and I'm sure you'll definitely understand. Now what if you cannot actually consider two terminals at all in the first place? Let's say you have a sphere like this. Now where are the two terminals in the sphere? In this case, the potential V refers to the potential of this sphere with respect to infinity. So basically the second terminal is taken to be at infinity in case of isolated objects. So if the capacitance of this sphere here is C, in that case C is Q by V, where Q is the amount of charge that must be added to this particular sphere to raise its potential to V with respect to infinity. Understood? So that was the first point related to capacitance that you had to understand. The relevance of the potential V. The second point that I'm going to talk about is not exactly related to capacitance, but it must be understood by you for future concept clearance. You see, it's basically about what happens when you join two bodies with different potentials. So let's try to understand what happens when two bodies with different potentials are connected together, because this concept is important to understand more about capacitors in this chapter. So let's say we have this body which has a potential V1 and another body which has a potential V2, and now I've connected both these bodies with a conducting wire like this. Now what you must remember is that when we do this, charge will be transferred from the body having a higher potential to the body having a lower potential until the net potentials of both the bodies are the same. So as you can see, this charge is being transferred from the body at a potential V1 to the body at a potential V2, and now both these bodies have the same potential V. So this will always happen when you connect any two bodies at different potentials with a conducting wire.